Yeah, thank you for the nice introduction and welcome everyone. So, yes, indeed, this talk is at least in part about this Spinnaker 2 and Spinnaker 2 system at TRDS and also which is called the Spin Cloud. But I have put a few remarks on neuromorphic hardware in general up front to give some perspective on this hardware system and also some outlook in the end to see where I see some fruitful directions actually for future developments. So, but let's just jump into it. So, if you have attended the seminar 2 weeks back, then you know already a bit about neuromorphics from Katie Schumann, from the kind of computational side of things. I want to take now here a kind of a hardware perspective on the whole thing. So I have a background in chip design, so I view everything a bit from that angle. And yeah, neuromorphic, as you might know, is tasked with investigating how we can take over knowledge that we know about the human brain and how it processes information to apply in integrated circuits or in hardware systems, as we say, and also learn a bit from building those systems as well. We can do this on many different levels. So our brain is a tremendously complex organ. So we can really go from single elements like ion channels or synapses and neurons up to the whole brain. And actually, there is in the middle, in between kind of the global scale of the brain or brain areas and the local scale of individual cells, there's not so much knowledge actually because we cannot observe on those scales. So we can measure individual neurons and bunches of neurons, and there's a detailed understanding of those. And we can, thanks to for example, fMRI or EEG, we can measure on the global scale, but in between there are several orders of magnitude that are difficult really to catch in measurements, and then thus we have to somehow make up some models or so to bridge between those orders of magnitude. So now this is just the neuroscience side actually, and now we want to kind of strip off maybe all kind of the biological details and use this for a technical application. So we have to make a choice essentially on which level we want to actually kind of rebuild what the brain does or mimic what the brain does and try to make use of it. And just to pick out two core principles that have been in the neuromorphic community for decades actually from its beginning, it's one observation that's really on the, at least in my sketch here, on the lowest level on the ion channels, is the observation that essentially a single ion channel or the behavior of an ion channel is quite similar to a single transistor when we operate it in subthreshold operation. So subthreshold operation is actually something, for me as a circuit designer, it's a pretty uncommon operating range. Normally you would operate your transistors kind of above the threshold, but there is really this intriguing similarity. So people have been building a lot of neuromorphic systems using this subthreshold circuit technique. So that's one thing. And if we go one level up to the synapse level, then there is the observation that essentially the synapse has computation and storage merged. So it means we have some properties of the synapse, so the coupling between two neurons that governs the strength of the synapse or its kind of synaptic weight, as we also say, and at the same time it transports the information from one cell to the other, so it also does the computation. And this is in stark contrast to the typical computer architecture that has a separation of memory and processing, for good reasons, of course, but it's not what we observe in the brain. So those two principles are really, I would say, at a lot of arguments in the neuromorphic community. But now, if we look at kind of more some available bigger scale systems, okay, the list is not complete, but at least those are systems that in my regard have achieved a remarkable size. Then you see that many of those, or the majority of those, actually don't use those principles, which is a bit surprising. I have put here two more. Yeah, so you see on the top left, you see the subthreshold I just talked about. Then connected to this is really analog computation. So you don't use digital circuits, but analog ones. Then we have the merged weight storage and computation, as we see in synapses. And another thing is that people postulate to use asynchronous circuits because they say, okay, a clock or a synchronity is not what we see in the brain, and it's an unnecessary overhead. But now you observe that essentially many of those systems don't really make use of those principles. Yeah. So, and this comes maybe in the first place as a surprise, but I want to make an argument for why this is so, because you see at the bottom line, also Spinnaker is not using those principles. I have to say, unfortunately, because of course they make up for part of the efficiency of the human brain, actually. Let's revisit those two ideas. First of all, for subthreshold circuits. So point is they use super low voltages and currents. That's nice because you can build super efficient information processing systems, at least in theory, but the practice says something different. So the point is here that you have an exponential relationship between the kind of the controlling voltage and the output current. And that means if you look at the diagram here on the right side, if you essentially change the controlling voltage by plus minus 4% in this example, you get a difference in behavior of over a factor of 2. So it's extremely hard to control those circuits, and also any variation in your process or in the supply voltage gives you a kind of high differences. So it's really hard to control those neurons, and therefore they haven't been really scaled up to significant size. And also, like in our brain, we have a high temperature dependence. So then your circuit kind of gets fever, yeah, if you operate it with too high temperature. So that's really tricky. And the way out that people have used is just use other circuit techniques, other analog circuit techniques, or moving to digital, because those, specifically digital circuits, we have an industry flow for implementing those circuits robustly. Then let's move on to this kind of statement that synapses have joined storage and computation. Yeah, but okay, I just picked now the example of the Spinnaker system, which I will go into detail in this talk. And if you look at the system architecture, you see, okay, we have actually a separation of memory and processing. So you see it already here in this layout figure. So all those structured blue areas, this is memory. In fact, it makes up 85% of the silicon array for each core. And so we have the separation. And then you see also we have an interface to an external DRAM. So this is the prime example of a von Neumann bottleneck. So you may ask, okay, what the heck? Yeah, you're building a neuromorphic system and you have von Neumann bottlenecks. Well, there are practical reasons for this. So you see in each of those cores, or there's 4 cores here. So in each of a quarter of those, we just have 128 kilobyte of memory. So it's really tiny. And often in applications, we are memory limited. Yeah? But still, we have 85% of the core area essentially is just memory. And this is already an SRAM is by around a factor of 10 more denser than if we would build the same with ordinary logic. So at least if we stick to digital circuits, we are ready by separating out the memory, the SRAM here from the ordinary computation, we gain a factor of 10. And then you can have a comparison here between one Spinnaker chip, which has like around 19 megabyte of memory, and an external DDR4 memory that we have in the system, which is 2 gigabytes. So it's more than 100 Spinnaker 2 chips. So we could stick to kind of the theory and spend 100 Spinnaker chips for this amount of memory, or we just place an external DRAM, live with the fact that we have a von Neumann bottleneck, but for many applications that need a lot of memory, like a general spiking neural network simulation, then this is actually the much more efficient solution. So, and I say this is unfortunate because we also pay a lot of energy, of course, in transferring this data from the DRAM to the chip. So what are the other ways out? Of course, we can start compressing models so that, for example, use some ordinary compression techniques or use sparsity exploitation, so skipping 0 entries. There's a lot of hope in kind of embedded NVMs or non-volatile memories, or those what people also call emerging memories or memoristive devices. So tons of names out, also different candidate technologies. This may be a way out, but it's not. If you really want to have it with a high integration density, it's not as mature as you want to have it at the moment, or the good part of the neuromorphic community does stick to a small size or kind of edge devices. So you see that the theory is the one thing and kind of postulates and good ideas, but you have to really check in practice. So let's see, especially these ENVM technologies, whether we can get finally really emerged computation and storage. That would be really cool. For subthreshold circuits, I have not much hope actually that they will make it in the future. Okay, so this sticking to small size that many groups do, I mean, it's fine for whatever applications near the sensor, but we really want to, if we really want to go to kind of the hardest problems, I would say, in the machine learning community, well, we have to look about scaling. And there, of course, is the property that essentially the bigger the models, the better they perform in general, which causes a lot of course pluses in the energy bill as well. But that's a general trend. And we have two trends. So there's one thing is the trend to bigger models, and the other trend is that more people want to use those models, the more successful they are. And of course, you all know that this is really a driver for energy consumption, and we have to work on this. So of course, the question is, can neuromorphic computing essentially bring a significant gain? But for really to showing this, we have to scale it. And that's exactly the point where we, in our group, together with the University of Manchester and the group of Steve Ferber, have been working for the past 11 years now to build really a large-scale neuromorphic system. We coined it SpinCloud, but it's essentially based on the Spinnaker 2 chip architecture. And Spinnaker 2 itself, as the 2 indicates, is the second generation of this Spinnaker architecture. The first generation is available already as a pretty large-scale machine at the University of Manchester. And the SpinCloud is using essentially the second generation chip, and its scaling target is to be at least 5 times bigger than, in capacity at least, than the machine in Manchester. So we have 5 million ARM cores with accelerators in 8 server racks. I have a few photographs later on. Actually, the design goal is 10 million cores. Let's see whether we receive the financing to reach this. But already operating 5 million cores will be a challenge, of course. So this is 35,000 chips and 400 kilowatts. So that's just to show you kind of the order of magnitude. Yeah. And if you do a kind of an order of magnitude estimate, then we have a capacity of simulating around 10 billion or even more than 10 billion spiking neurons in real time if they are simple enough. Some points from the hardware perspective I want to make is that if you want to build a large-scale system, it's maybe a no-brainer. The single components need to be reliable. So this is a bit in contrast to some neuromorphic systems which are more experimental. And in my opinion, why they can't be scaled up is partly due to the fact that they cannot be operated reliably on a small scale. And then if you have many of them, you just essentially run into the curse of complexity. So you can't control them. The second thing is that I said already, we started this 11 years back. We are now at the point that we have the hardware standing there, but we're still in the process of bringing it really into operation and have all the software at hand. So it's really a significant investment in time and in resources. So you don't build this just for one use case, unless the use case is really, really super important. So you need flexibility and you need a lot of software to make it usable. And this is kind of, maybe not the super cool scientific test cases or so, but it's a lot of engineering, but you need to do it. And this is, I think, true for any large scale system, but now the neuromorphic part of it brings more challenges with it. So you have to compute with spikes or kind of events. We'll come to this. So we have a lot of workload variations, which we have to cope with. And if we still want to be energy efficient, despite those workload variations, it means we need to minimize the baseline power of the chips. This is also a challenge that we have to work on the hardware side. So this is just some photographs of the Spinnaker system. So we have now, since 2 months or so, we have pretty much all boards, almost all. You see some are missing here. We have them installed. We have the infrastructure up and running, but I have to do a lot in terms of the user access software and operating software for running larger scale simulations. So single board level we are currently supporting, but bigger, this is still work in progress. You've seen already maybe this hint that we have the von Neumann bottlenecks, for example, and apart from that, also it looks like pretty conventional, right? So what makes Spinnaker 2 actually neuromorphic? And I tried to somehow summarize this This is, from my perspective, a philosophical question, because anyway, if a system is useful, then okay, who cares about principles? But what makes it, from my perspective, makes it neuromorphic is that we have really many tiny compute elements that operate independently and in parallel. So this is like our neurons in the brain. We have really an adaptation to the workload. So also our neurons are kind of spiking more heavily or less heavily from time to time. And we have actually a communication with spikes, or more generally with events. So it's not that we communicate large chunks of data, but we just communicate when something happened. And this is what we call an event. And this is essentially 1-2 abstraction levels higher than what I showed in the beginning. So this is more a platform for algorithm development and trying out new types of algorithms, both from the neuromorphic community, but also for any kind of algorithm that you want to run, which benefits from this architecture of many tiny compute elements. Let me jump a bit also into the architecture. I don't want to go too much into detail, but to give you some glimpse on how it looks like. So the majority of the chip is comprised of these 38 so-called quad-core processing elements, or in total we have 152 ARM microcontroller cores, which can run any software. So essentially also models are implemented in software. Then we have dedicated hardware accelerators for neural networks, and we have some dynamic power management infrastructure so that you can adapt to the workload. And then we have all kinds of interfaces. So there's a host interface. We have chip-to-chip links for building a larger scale system. We have the external memory, and we have some periphery. And most notably, there is in the middle, there's the Spinnaker router, which essentially allows us to send around messages between chips. Okay, so for design purposes, this is everything is kind of connect by place. So it means essentially you just design this one here and replicate it all over. This was a necessity to get a chip of that size done with an academic group. And you have at least no global synchronous clock, so everything runs or asynchronous on a global scale, but synchronous on a local scale. And you have some also communication infrastructure on the chip. Kind of this is the global architecture, but if you look inside a single processing element, so you have a core and some tiny bit of memory, 128 kilobytes, but then you have also those accelerators that you can use for speeding up workloads that are related to neural networks. So you have multiply accumulate accelerator, so you can run kind of typical layers of deep networks. You have what we call neuromorphic accelerators, or for spiking models, so exponential and logs functions are there, used very often there, and also kind of some noise processes you can model with random numbers. And then you have some infrastructure also for this event or spike handling. Specifically, these MEC accelerators in each processing element, just to give some details here. So you have, it's like a pretty ordinary kind of deep network accelerator. It supports matrix multiplication and convolutions. You have an array of MEC units. There is a support for different parameter resolutions. So you can have a trade-off between the kind of resolution and throughput. And the point I want to make here is that really it's a small overhead in terms of area and also the kind of the baseline power. But not out of a sudden, but essentially this allows to run essentially also deep networks on the chip with pretty good energy efficiency. So this is, I mean, it's of course not among the top energy efficiencies in the literature, but it's not too bad actually. Here are some characteristics. So first of all, baseline power of the chip is just 1/4 of a watt. So this is if you really would be able to run a program on all the PEs, but you're not actually executing it at the moment. And then you have to mention here, you have 2 performance levels. So PL here stands for performance level. So one that is allowing for higher energy efficiency and one that is allowing for higher throughput. And you can see it, for example, also here if you just look at the network performance, you either can have a higher throughput in terms of teraops per second, twice the throughput, or you can have a better energy efficiency in terms of teraops per second per watt. So one can switch depending on the task essentially between those two. And this is also actually something that we tried out for spiking neural networks, where you have this fluctuating workload. And essentially each PE can do the decision on how fast it needs to process information in the near future. It can do it essentially autonomously on its own by some piece of software. And the switching happens very fast, so below 100 nanoseconds, which means essentially it's almost transparent. And then what you get is you can run, for typical workloads, you can run essentially your processing elements at the lowest power level and only switch to the higher power level in a few simulation cycles. So essentially you achieve the same performance as you would if you ran everything in the higher performance level, but you get around a factor of 2 reduction in the power consumption. So that shows you the benefits of this kind of fast workload adaptation that we can do with spiking networks. And then lastly, we have essentially the established Spinnaker communication network, which, just to mention 2 things mentioned, is meant for very small packets, so not sending around big chunks of data, but it's really meant for small chunks of data. And it allows for multicasting, which is also something that you observe at the brain, where essentially one neuron is connected to a few thousands of others. And this you can very nicely implement with such kinds of architecture, right? And then there are some things that we learned from Spinnaker 1. So first of all, you have a variable payload, so you can also send those spikes with some value or some data, which is nice for some algorithm development. And you can also have a more efficient point-to-point data transfer. Actually, already in this relatively early state of deployment, still, we have a range of applications which are maybe not super obvious. So there's high throughput screening of drugs or virtual screening of drugs to select good candidates for future medicine that you can test in the lab, which requires to run very, very tiny deep networks. And as we have these tiny compute elements, this is a nice fit. Then we have some event-based deep learning algorithms. I will show in the end, I will show 2 examples for that, where we, due to this event-based nature, are more energy efficient than ordinary GPUs. And there's also some, maybe, I don't know, not so obvious use cases that are currently evaluated. So one is optimization and the other one quantum emulation. So you see one can also make use of this kind of architecture for non-neuromorphic use cases. Okay, and just to mention, there's a recent development in the community which is called neuromorphic intermediate representation. So if you're looking at deep networks, you have this exchange formats like ONNX, and this should be a counterpart also for spiking networks. And we are part of that community and supporting this. So if you have spiking networks, essentially, then it's good to use this intermediate representation. Then you can train those networks on whatever arbitrary spiking network software frameworks. Okay, so that's all I wanted to just give as intro for the Spinnaker 2 development. Of course, we can have some more discussion on this. And I just want to conclude with an outlook, because from my perspective, still in the field, there's a lot of kind of, at least felt, kind of rivalry between deep networks and spiking networks, or it's viewed as kind of just those 2 solutions. So you have the deep networks, which run on power-hungry GPUs, and then we have if we make it spiking, we can run it on super energy efficient neuromorphic hardware, and it will be all better. But actually, this is, first of all, is not true for a lot of use cases, because if you scale also spiking networks up, they also will burn a lot of power. So it's not clear. And also this kind of that you just have spiking networks, I think is just too short a view. Yeah. And there are works in the community, and I just picked 2 from our group that try to kind of explore the world between the artificial neurons or deep networks and spiking networks. And this is what I would call kind of event-based computation. So it means instead of always sending a value out of for example, a recurrent neuron, as in this example, you just check whether its value changed, and then only then, when it changed significantly, you send out a value. So that's one way of making a continuous stream of data, kind of what we call event-based. So you just send out a new data if something happened. So that's the philosophy. You can also train those networks, and the point here is that essentially you can achieve the same performance as with a kind of conventional recurrent neural network, but you need 80% less communication in the forward path, and also I think with more than half of the communication in the backward path. So which means essentially you can, which makes scaling those models easier actually. So, and these are not spikes, these are really events that each carry a scalar value. And if we look at the results, so we implemented this on the Spinnaker 2, that's mainly work of my colleague Khalil Khan. You see essentially that you can outperform in NVIDIA AI100 in terms of energy, not in terms of speed, of course, but in terms of energy, because on the architecture like Spinnaker, you can make use of this reduction in communication. So I have to put a disclaimer here that this is also this is true for a kind of a batch size of 1. So if you really want to have something like an online processing, this is a nice match. A GPU gets more efficient and eats up this energy advantage if you go to a higher batch size. So that's also, you see that one can essentially utilize the different systems for different parts of an application. So you could do some kind of pre-training on a large data set on a GPU. And then if you want to move to a more online use case, then you can move to a more neuromorphic system like the Spinnaker. The second example, this is an example from my colleague Mark Schöne, are event-based state space models. So state space models is a developer they have received more attention recently because they can be trained quite nicely, or they can be parallelized also in training quite nicely because they have a linear feedback in contrast to previous recurrent neural networks. And this work here is about really operating those models in an event-based fashion. So you can directly use data from event-based sensors, feed them into the model, and yeah, can fully utilize this. And this is in contrast to most of other works, which essentially just take the events from an event-based sensor, but put them into frames again, and then feed them into an ordinary neural network. So, and by this kind of native support, you can also gain efficiency. So this is an example from this first paper on this, and on 3 commonly used data sets in the neuromorphic community at least. And you see that for the 2 left, or the left and the middle one, this kind of model is outperforming the state of the art. And on the right one for the DVS gestures, it's doing pretty well compared to the state of the art. And it even allows for smaller models because these recurrent models tend to be quite efficient. Unfortunately, I don't have numbers yet for the energy. If we would implement this on, for example, a Spinnaker or another neuromorphic system. But you see already that from the model size that essentially this looks quite promising. So yeah, take home message here is essentially there's a lot to explore between those kind of pure spiking neural networks or artificial neural networks. And I want to conclude with an observation. So if we look at our brain again, and we assume this is here in the middle, this is the small print. So we assume some order of magnitude characteristics of our human brain. Then if we do the computation, we arrive at 10 to 100 teraops per second per watt in terms of energy efficiency. So this, if you look at works for deep neural network accelerators, this should look quite familiar. So kind of really the best accelerators achieve this value, or even are better than this, even by some by an order of magnitude. So what has, at least from my perspective, what does it tell us? Well, on the single operation level, we are already on human brain efficiency. It's more that we have to understand how to orchestrate those individual computations and to have a fixed essentially communication and model scaling to really achieve also the whatever 20 watts estimated power draw of a brain in a technical system. So on a single macro level, on a single core level, we are already there. From my perspective, so the challenge will move more towards the upper levels of abstraction. I don't think that neuromorphics is just, an isolated field, or it will whatever solve the thing alone, but I guess we will see kind of really the best model somewhere in between. So we have this spiking networks, spiking computing architectures, but we also have outside neuromorphics in the deep learning community, we have this big field of sparsity exploitation. So where you essentially just scratch zeros or try to generate zeros and scratch them. And this is closely related actually. I think that there can be a good exchange between those. And on the lower level, we have in the neuromorphic community these many groups that work on memristive devices and also in memory computing, which is along the principles of our synapses, merging computation and storage again. But this is also there's also a drive in industry actually about those types of memories, and also a drive to in-memory computing. So I think also there it will be an interesting exchange in the future, I think. Okay, that's all I have to say. Those are the people behind the Spinnaker brain. And yeah, thank you for your attention, and I'm happy for questions or discussion.
I'm going to start, fire up my list of questions. So first of all, the Spinnaker 2 cluster has a maximum power, you stated in one of your slides, of 400 kilowatts.
Yes.
At 35,000 chips, that's like 11 watts per chip. And then on slide 20, you stated baseline power per chip of 250 milliwatts.
Yes.
That's a huge dynamic power range.
Okay. In fact, it's not as huge as this suggests.
Okay.
So but there's still, I mean, there's still a bit more than an order of magnitude. This scaling target, or the power budget essentially that we have in the room and in the infrastructure, was for the 10 million core system. So it has twice the number of chips. So we are at 70,000 chips then, and this gives still like 5 watts of peak power. Those 5 watts is essentially what we estimated as absolutely worst case from chip simulation. So it was at the time where the chip even wasn't manufactured. The most that we measured so far, if I'm not mistaken, is something around, I think, 2.5, 2.6 watts. So actually we overestimated this. Yeah, but still that's the budget. Yeah, I won't burn my hand whether we can't find another use case that takes more power. But still, you then still have an order of magnitude baseline towards peak power. Yes.
Does that constitute any technological challenges? Because, I mean, standard server chips in the HPC area also have a lot of dynamic behavior in their power consumption, but the baseline power is much higher.
Yes.
That's half of what the TDP is. And here, with one order of magnitude between base power and max power, is that a problem on the electronics side?
Well, I think you always design for the peak power essentially. So and then if you burn less, it's generally not too much of a problem, but you may lose essentially this kind of efficiency. So even if your chip itself would only burn like 250 milliwatts, then if you build your voltage regulators, for example, for the peak power, then they also have a higher kind of baseline cost or baseline power essentially. So that's a bit a challenge. That maybe the benefits that we could have on the single chip level cannot be transferred as well to the system level, because we always have to design for the peak power. So that's still a challenge. We have some initial thoughts on also building a kind of voltage regulators on chip, where we have more exchange and more control over them. But this is still in the very initial stages.
About the network, it looked like the network is really optimized for small payloads.
Yes.
So, well, the limit of that would be actual spiking neural networks. But on the other hand, could I run a standard MPI program on it, or would that be horribly inefficient because the network isn't up to the task, sending normal MPI messages, which could be kilobytes, megabytes, or more?
Yeah, the point is that you have to split this then to messages with 128-bit payload, and then you have the addition of the key, like 32-bit, and I mean this is in itself, it's an overhead, and then of course each of those spikes is handled on the chip separately. This is not so much of a problem. I think the main bandwidth limitation is really in the links between the chips. So we have just 2 gigabyte per second links between 2 chips, which is not much. Yeah. So then I guess you may run into a bandwidth problem. And my other question would be whether you can do an MPI implementation. I don't know, yeah, but just to mention whether you can do an MPI implementation in the code size of 128 kilobyte.
Yeah.
So it also, you don't have an operating system. Yeah. I mean, of course you can have some elementary one. Yeah. But this is code that you write for the system essentially is really, it's kind of difficult because you cannot rely on a lot on standard libraries because they're just too big.
Well, like programming an Arduino chip.
Kind of, yes.
Yeah. Now, still about the benchmarks you ran already on the system. From your experience, I mean, the choice of this Cortex M4 core, that was, I think, a compromise between performance and power, probably. You could have chosen maybe different architectures.
Yes,
but
that's true.
From the applications that you already ran on this platform, is the computational performance of the chip a bottleneck, or is it actually overpowered, or is it just the sweet spot?
It depends a lot on the application. So, I mean, if we just talk about the processor, so for what I showed for this eGRU implementation, this is just running on the processor, seems to match nicely. So that's okay. But as soon as you run kind of the Mac accelerator, you have a much higher speed in processing information. So if you run a deep network or a layer on it, we typically are in the range that we could do much more computations, but we don't get the data, or we don't have the data locally. And then we would have to load it from the external DRAM, and then we really run into the von Neumann bottleneck that we can't get the data fast enough from the external DRAM. So that's an issue. I mean, it was not designed for deep networks in the first place, but essentially, if you would to really operate it really efficiently, you would have to have all the data in the local SRAM. Then it's okay. For spiking networks, it's a bit different because typically the models are run in software. Then kind of this memory and compute balance is better. But if
you had targeted only for spiking neural networks, you could have gotten away with smaller cores maybe, and many more of them.
Why? I mean, the point is we can map around 1,000 neurons or so on each core. And
necessary computations. I mean, the Cortex M4F has floating point units.
Yes.
Do you absolutely need them in all scenarios?
Not necessarily, but if you want to be flexible with the models and not to have too much headaches in the software development, then you want to have floating point. That was actually something that the Manchester group, working with the Spinnaker 1, was really, really insisting on. We need a floating point unit because they had modeled. I mean, you can emulate, of course, floating point operations, but then you need for each elementary operation, you need more than 100 clock cycles or so, and this makes it really slow. So yes. At least for flexibility, it's good to have. And it actually doesn't cost much in terms of area.
Okay.